Benford's law. So what is Benford's law? It's a formula that gives us the percent abundance of the first digit of each number as the data set goes to infinity. This is the formula right here. So I don't even know if this is statistics or not, but I found it really cool. Because the logic behind it is pretty simple. And I'm gonna explain it using Sketchpad over here. Okay. So let's say you have a data set from 1 through 3. That means 1 has a 1/3 chance of appearing one time using some basic proportions. And as this is going to infinity, or getting bigger and bigger, let's look at the first digit of each number. So now the first digit of each number has a chance of appearing 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 out of 20 times. A way higher probability, right? But now we can scale this up all the way to 100. And I'm not going to actually draw that out, so you're not going to have to see that. And we'll scale that up to ... It's going to go all the way to 100. Now everything is equal probable. There is there is 11 out of 100 of each one. So 11 out of 100 twos, 11 out of 100 threes, 11 out of 100 numbers that start with 4, so on and so forth. Also, if we use an expansion series, or if we use summation, I don't know why we wouldn't get 1 actually. That's a little complicated, but I'll look into that later. So you notice that the probabilities become more equal as n is approaching infinity. But you notice that past a certain tipping point, what actually occurs is that smaller numbers appear more frequently. So, let's delete all this first. Let's just delete this. Simply adding 3 numbers at the end gave us 4 more digits of 1, of numbers that start with 1. So that gives us 4 over 12, 1/3. That's a way higher probability than anything here. And to equalize it, we have to go to 100 to have things that start with 9, like the 90s row. We have the 80s row, we have the 70s row. But since these aren't present with the data set of only 12, because smaller numbers appear more frequently, because for it to be equal probable, it has to have all an equal amount of 1s, 2s, 3s as the starting number for each data set. But then once you even slightly go past that, it's going to favor the small number again. So like if you go to 101, 102, 103, 104, it's favoring 1 again until you get to the 200th place, which 200 becomes equal probable. Then you pass the 200th place, 300 becomes more equal probable. So that's the logic behind it. I'm trying to find a simpler way to explain it because I didn't rehearse this. But for something to be equal probable, all the things have to appear once, or all things have to appear the same amount of times. But once you reach past a certain tipping point, like 10, you now need to go to 100 to equalize everything. And then for 100, you have to get to 1,000 to equalize everything, and so on and so forth. So this brings us to Benford's law. Let me copy this, bring it over here. Oh, it's invisible. Okay, well, I'm just going to have to write it out. I should have memorized it, actually. Probability, and I don't know whether to just say PD because that's the probability notation in statistics. 1 plus d to the minus 1. Actually, that's complicated. Let's just do 1 over d. So this is a quite easy formula. You plug in the number that appears once. You plug the number that appears at the beginning of a number, and it tells you the probability of that occurring in a data set. So let's say 1. Let's do this, and we'll do 1 plus 1 over d, which gives us a probability. Oh, sorry, d is 1 here, actually, because we were plugging in 1. And that's going to give us log 10 2, or I'll just write log 2, I guess. If we do that for 3, you'll notice that as d gets larger, the probability gets smaller of it being the first number that appears. So the logic being that smaller data sets will make this overall term larger because it's on the denominator and it scales downwards. So this is the highest it's going to get, log 2. I mean, I guess 0, I mean, that's undefined. So 1 is this. I think it's only for energy values as well. I mean, yeah. Yeah, how else would it be decimal values? But yeah, log 2 is the highest probability that a number appears in a data set. There's also a chart where you can find the probabilities of each number appearing in a data set. But what are the implications of this? And the implications of this are security fraud and measures. I'm not sure how that works because they'll probably take some calculus or something, but you'll find that online. This is just a simple overview to Benford's law. And yeah.